Okay. Okay, so welcome to everybody. So today we are happy to have here Flora Koukiou from the University of Cergy, and she will talk about the freezing and entropy of logarithmically correlated Gaussian fields.
Thank you, Margherita. Thank you very much, the organizers, for this invitation. I'm very pleased to speak to this seminar. I would like also to thank all the organizers present and the former for this successful, very efficient series of seminars. Today, I'm going to discuss a relation between the freezing and the entropy, the specific entropy, for a class of Gaussian fields. Those correlation function decays logarithmically with the distance. The freezing, can you see my? Okay. The freezing is a concept, also a property, describing the low temperature behavior of random systems and can be manifested from the linearization of the free energy for low temperature. So after some freezing temperature, the free energy become linear. It can also be manifested by the domination of the Gibbs measures by the local extreme values of the random fields. This gave rise to the terminology of glassy phase, very popular among physicists. In this talk, I'm going to show that freezing can be as well defined, characterized from the behavior of the entropy of the Gibbs measure associated to the potential. Namely, we'll see that the freezing is equivalent to the vanishing of the entropy of the associated Gibbs measure. I'm speaking here about the specific entropy. The first study of freezing was made more than 40 years, a long time ago, by Derrida in the totally uncorrelated case, in the case of the random energy model. I think everybody here knows the random energy model. It was a very simple situation, but the freezing has observed, studied, and the random energy model, although so simple, played in the following a very considerable role to our understanding of more complicated random models. Some years later, Derrida and Spohn in 1988 introduced a study, random polymers on trees. They put random potentials, IID random potentials on its bond on a binary tree, and consider self-avoiding walks. This was the first model, non-trivial, where the freezing transition has been studied. And this model, although so simple, it was enough rich because it contains the non-trivial logarithmic correlations. What Derrida and Spohn did is they show that a suitable generated function of the partition function converges to a traveling wave. I have to add that they didn't study the discrete model, but a continuum version of the model using the Bramson's work and the Bramson's result, because Bramson has already showed that this model, the continuous model, has a freezing transition, a critical freezing transition, and at which the system is frozen. As a discrete case of this model has been visited only recently, many years ago, by Webb, who considered the discrete case, and he proved freezing, and also he showed that the discrete case behaves as the continuum one. Now, these first results, they followed by several other studies where the freezing has discussed in the mean field models, very popular studied by physicists at this time. Let me just mention some random multiplicative measures on trees. This work has been inspired by the Gaussian multiplicative chaos introduced by Kahn at the mid of 80s, the director polymers of the trees. And there is a series of work where the freezing transition have been discussed extensively by Fyodorov, Bouchot, and Fyodorov and Ledoussal, where the freezing has been related to the extreme value statistics in some log-correlated versions of the random narrative model, and also it has been related, this is very interesting, with the multifractality properties of the measure, and also the random energy landscapes. In 2001, Carpentier and Ledoussal made conjectures based on non-rigorous arguments that the freezing is a generic property of long-correlated Gaussian fields. On the other hand, in mathematics, the long-correlated fields are under intense research investigation even now, because they share many properties with the Brownian random Brownian motion. And mathematicians studying these fields, they found several links with the freezing transition. One can mention the case of Gaussian Brownian random walk of the work of Webb, as I said. Recent work by Subak Zeitouni, where they show that the decorated Poisson process, they study the limiting extreme process of this decorated Poisson process, and they study the freezing, they have a freezing behavior. And more recently, for a subclass of star scaly variant fields, Madole, Rhodes, and there is the other Vargas, they shown the freezing transition for a very general class of log-correlated fields. So it seems that this conjecture is true. So there are several other models to be studied, but in principle for physicists it's true, but mathematicians recently have started to prove this conjecture. Now, a question I can ask now is, can one relate the freezing property with the behavior of the entropy of the associated Gibbs measure? The answer is yes. We can show that the freezing transition can as well defined from the vanishing of the specific entropy of the associated Gibbs measure. This can be verified in some mean field models like the REM. Of course, it's not log correlated, but still it is an interesting model to check. It exhibits freezing on random polymers on trees in the case of multiplicative chaos, and also in the mean field spinning glass models. In order to give unified treatment of this model, I'm going to define a generic Gaussian model as follows. You start with a finite alphabet, start taking two letters, contain only two letters, A and B, and we can form words of length n. Here I stop only in the words of length 4 because it's very long. To each word, so each word is a configuration, as you can imagine. We can associate random Hamiltonian. The random Hamiltonian, the explicit form of the Hamiltonian depends on the particular model. So if you like to define the REM model, it's sufficient to associate to each leaf of the tree. Note this is a mistake here. The leaves of the tree, random Hamiltonian, this is not the nodes, the leaves at the end of the tree, because we have independent random variables. If you like to define the multiple chaos, the random polymers of the tree, you need to define IID-centered Gaussian random weights indexed by the edges. And in the case of the Shelton-Kilpatrick-Millfield spin glass model, we define a family of IID-centered Gaussian random interactions indexed by the pairs of levels. And here I'm giving just an example of the Hamiltonian of the SK, the Shelton-Kilpatrick model, for only N4 sites. You can see. So a configuration is like is the red line. In the previous models, in the case of polymers of the trees, the interactions, so the interactions are on the edges. We have a multiplicative, Hamiltonian is given by the multiplication of the interactions of the edges, and the model is not trivial because we have correlations between the paths. So we have several paths on the tree, and the correlations are induced by the paths having common parts. Now, for all models, so all the models can be entered into this scheme. And now we can define the Hamiltonian as usual. And the partition function, here you can see that I'm giving a tilde partition function. It's a partition function having a strange normalization. This normalization is important for the following. I'm defining the annealed free energy, the quench free energy, the thermodynamic quantities as usual, the entropy, and all these thermodynamic quantities are random because it depends on the realization of omega, and the natural question we can ask, what about the possible limits when the n goes to infinity, that is the thermodynamic limit. What we can say about the existence results? The results, all the models, of course, undergo phase transition. The existence of the free energy is established rigorously for all the models. This free energy is called Kemp's because it's valid for all realization of the disorder. It's not random. The entropy, of course, the specific entropy exists. And here I'm giving the relation between the quench free energy and the specific entropy. This relation will be useful for the proof. The critical behavior is characterized as usual by critical temperature, and here because we have, where the Millfield regime, we have this nice property that the quenched annealed free energies are equal before the critical temperature. So we can use this definition for a definition of the critical temperature up to the critical temperature, the supremum of the betas, up to which the two free energies annealed cancelled are equal. Now immediately it follows that the quench energy must be lower than smaller than the annealed one by the simple concavity of the logarithm. Moreover, we can define a freezing temperature by the minimum of the betas for this from which the specific entropy vanishes. So it's just a new definition of the temperature, a freezing temperature. I anticipate your question, what is the relation between the critical temperature and the freezing one? In the majority of the models, as you can see, the critical temperature and the freezing temperature are the same. So there is no difference, not for other models. So the theorem, what I'm going to show in this talk is the following. The freezing temperature for all the previous models cannot exceed this particular value of beta, noted beta star, equals 4 times the logarithm of 2, is a number almost 2.77. And moreover, we have that for each beta, beyond this beta star, the specific entropy of all models vanishes. That means that for all of our models, the freezing entropy belongs to this interval. The critical temperature is proved there is bigger or equal to 1. The free agency is between these bounds. And I'm remarking that for the 3 class of models, REM type, polymers of tree, or on trees, or multiplicative chaos, the free energy and the freezing energy coincide, and we have that the specific entropy is 0. That means at the phase transition, the system freezes, and it remains frozen, of course. For the mean field spin glass model, the Sheraton-Kilpatrick, the critical temperature is 1. But at 1, at the critical temperature, the specific entropy remains positive. It is easy to calculate. We know the value. Hence, the freezing temperature of this model is bigger than 1. I'm recalling, so this I can prove the theorem in the case of Sheraton-Kilpatrick. Why? Because for the Alvel models, it is trivial to prove, and we have all the gradients. There is no new results. The new results will appear here in the case of Sheraton-Kilpatrick. I don't think it is necessary to give all the definitions of the Sheraton-Kilpatrick, but just recall the original definition without external field. Just what we need is just to have the original definition of the model, with very old, is almost 50 years old model. We start with a countably finite independent copies of standard centered Gaussians arranged like a symmetric matrix. From a finite set of n sides, we associate one space to its side, and we defined the product configuration space. To each configuration, we associate the random Hamiltonian. As usual, we define the random Gibbs measure, where the partition function is here. You see is the standard partition function. I'm not using any normalization because it's the original, the model without any definition, without any normalization. So it's the original SK model. The first results, not rigorous at the, for the moment. I'm speaking about the results at the end of 70s, at the beginning of 80s. There is a phase transition of the model. It is expected that the free energy is self-averaging. That means that this is close to its expectation for large N. And Parisi proposed a replica symmetry breaking solution for the low temperature. What about the rigorous results on this model? The first rigorous results concern the existence of the quantity limit, and it's given for the first time, at 87 in 2 papers simultaneously, one on the one hand by Eisenman-Lebon-Ceruel and one hand by Friedrich and Zergaliski. The result is the following: for the high temperature region, that means that is for values of beta smaller than 1, the quenched limit exists, and moreover, it's not random. It is equal to the annealed mean, and it's given simply from this, because it's very easy to calculate the mean value of the partition function. That was the first rigorous results. So since 87, many new results. These results have been proved not only for the original version of the model, but also for many variants by adding external fields and similar models, etc. There are many nice works with many interesting mathematics achievements and techniques, but it's not the purpose of this talk to present all of them. So I don't know all of them, of course. What happened for beta bigger than 1? That means that for a low temperature, it was a very long study problem to show the existence of the quenched free energy. And the breakthrough came firstly in 2002 by Guerra and Toglianelli. They have used a very clever and simple interpolation argument to show the existence for every beta of the free energy. Later on, Guerra, Talagrand, and Pansenko show that under some conditions, the variational formula provided by the Parisi solution is valid, but not in the generality. So they prove rigorously the Parisi formula under certain conditions. Question. Now, what happened to the entropy of the model? The entropy, we know that the entropy is all the entropy of the Gibbs measures I mean. So the entropy is a decreasing function of the temperature. And it is expected that the specific entropy eventually vanishes. But there is no calculation. There is not the only in my knowledge, the only mention about the entropy of the low temperature of this model is 2 sentences in the work of Eisenman, Lewis, and Rel on the one hand, and Pasture Srebina on the other hand, saying that yes, the entropy in low temperatures vanishes eventually, but there is no other calculation or other indication. The high temperature entropy, specific entropy, is given from in this formula, can be calculated. So now we can. So before starting, let's pass to this proof of the theorem. And before that, let me just to start with a warm-up lemma. For all beta bigger than beta 1 is the critical temperature of the model. The quenched limit can be expressed by this formula, where the function S, the last term, is the relative entropy of the measure mu at the temperature beta 1 with respect to the measure at beta for every beta bigger than beta 1. The relative entropy is a positive function, is vanishing when the two measures are equal, and roughly speaking, give us the extent to which the measure at beta 1 differs from the measure at beta at every other beta. You see here, if you take the measures equal, the last terms is 0. This happens only in beta 1, and you recover the free energy, the quantum free energy at 1. the proof of the lemma is given here. I'm taking just the definition of the relative entropy. The first term, the limit of the first term is just the minus the entropy of the Gibbs measure of the specific entropy at beta 1. We have the limit. The last term is the quant's free energy. If you calculate, you obtain this limit, and if you replace the beta 1 but the value of critical the 1, you get this formula in red. Let me just comment this formula. This formula gives the quant's free energy for all temperature. This is appealing, the formula is appealing intuitively. Why? Because the first two terms come just from the convexity bound. Why? I'm just using the geometrical fact that every convex function, the graph of every convex function is above it's at its point of his derivative. It's very, very easy to get the lower convex bound. This last term describes the difference between the measures. It is much more simpler to understand from compared to the Parisi solution, because the Parisi solution comes from, of course, it's very elaborated, very nice, but difficult to understand. But unfortunately, the two formulas are very difficult to manipulate. For instance, it is not possible to calculate for every beta the specificity, the relative entropy, just to have the possibility, if you like, to draw, to have the graph of the functions, to see how look like. But as you can see in the following, there is a special value of the beta. One I have shown this in the theorem. At this particular value of beta, we can indeed estimate the specific entropy, the relative entropy. This is very nice, and it is shown the following. So the challenge, this result is a side product of a side result of this work. I think it's a real challenge how to recover the Parisi variation formula from this expression, or vice versa. But it's not the object of this talk. Now, if we come back to the titlet limits, the G's, remember, the G's came with this strange normalization of the partition function, are related to the real quant's free energy and nil free energy by this formula. And for the previous lemma, we have that for every beta, the G, the quant's tilde free energy is given by the free energy at beta 1 plus the relative entropy. And now I have to explain where the particular value of beta star comes from. It comes from a very simple, really simple observation, came out from accident. First of all, let's draw, we can draw the limit G annealed. We know the expression we can draw for every beta. This is the blue line. Then, if you draw a straight line passing from 0, the beta 1, remember, is 1, the point A, you continue, this red line cuts the, I'm sorry. I lost my cuts the annealed at the point A prime and defines the specific value of beta star. Nothing more, it's very, very simple. Let me also comment now the blue line, the annealed. You see, it's a convex function, of course. Its minimum arises at beta 1, the point A, and moreover, its slope at this minimum is 0. This is due to the normalization we have introduced to the Boltzmann factors. And this is a very technical facility for the proof. So we have the annealed, and now we know that the quantz is below the blue one and above the dotted line, because the dotted line is the tangent to the minimum by convexity. So we expect that the G infinity will be below the blue, and somewhere here it cuts the segment A prime C at some point. We don't know where it is, at some point C prime. That's all. And what I'm going to do is to calculate C prime C, which is the relative entropy. So we have an image here. What will be? It will be the quantz limit will be somewhere here, and it is possible indeed to calculate the exact, to estimate the position of C prime. For all beta, the quantz limit is given by this term plus here the relative entropy. But the relative entropy cannot be calculated everywhere except at this point. That's all. Now, what we have to do now is to try to calculate the relative entropy. And what I'm doing here is just, I can just estimate how close the C prime should be in order to have a lower bound. I need now to formalize a bit. So we have here, so the idea of the proof, so it comes for this, this image is very simple again to find the particular value of beta star. And intuitively we say, because we have a relation between the two annealed here free energies, must be some relation between the corresponding measures. And this is the case indeed, and this relation is provided by the relative entropy. Let me formalize the things. I'm defined mapping, and this mapping reads to the values of limits. The limits at, you see the limit, the annealed limit at beta stars, it's expressed as a function, it's multiplied, so we have it's mapping to the limit of, as a function of the limit at beta 1, which can written as the quantz limit plus the deviation from the annealed one. This is standard. And what I have now, I can back, we can see that here the segment A prime, C prime is the deviation, is called alpha is what is followed, and the C prime C is the relative entropy, and the advantage, and again, of the normalization I have introduced to the partition function is that the segment AB is not only the quantz limit G for beta 1, but also is equal to the specific entropy of the model at beta 1 at 1. So I can express everything in terms of the specific entropy of the model at beta equal 1 at the critical point. And I'm presenting the proof in 2 lines before entering to the technicalities. We have, remark for the lemma that the Quant's limit, the Quant's limit is the tilde, is given by the entropy at beta 1 plus the relative entropy. We are going to estimate for beta star, this is a beta star, a lower bound of the relative entropy, and we're going to show after that this lower bound is consistent only with the vanishing of the specific entropy at beta star. There are 2 steps. The first steps obtain a lower bound for G infinity at the point beta star. This lower bound but can be obtained always from this picture. I prefer to give this picture because I can give you a very short geometrical proof without technicalities. We have seen that the segment A prime C is the sum of the relative entropy plus alpha, which is the deviation of the free energy from the annealed one. This, thanks to the value of beta star and the geometry, it is easy calculate. It is easy to have the value of this segment. So who know the segment how is, so it's expressed very easily as a function of this segment. Now, consider if you consider this A prime C prime segment, the deviation, you can think if you transport this segment below the C, you can realize that it is not possible to go below the B due to the convexity. So the maximum value of the alpha, the maximum value of the segment A prime C prime must be this or this CB or AB. And thus that the maximum value of this provides with the lower bound of the specific entropy, which is given here. Remember that the G at beta 1 is given also by the entropy of at beta 1, and we have a nice, very simple bound of the Quant's free energy at beta star. The second, this is the first step, is quick. Now we can do more, saying that if the second, if the lower bound is saturated, can you go further? The answer is yes. Suppose that the lower bound is saturated, because you cannot calculate exactly the value of the relative entropy. We suppose that the lower bound is good, is saturated, and we consider the relative entropy of the Gibbs measure at beta star with respect to the Gibbs measure at beta 1. The relative entropy is not a symmetric function, so we have the 2 relative entropies, and this sum is given by this expression where the A infinity is given by this limit. If you remark this limit, what it gives? It gives roughly the difference between the derivations of the between the slopes of the two free energies. This is the physical meaning of this limit. It can be calculated. Now, using the inverse map, we can show that the maximum of this relative energy is given by this formula. It seems the two entropies at beta 1 and beta star are related from this from this equation. This equation at the maximum, given the lower bound is saturated, is consistent if and only if the entropy of if the specific entropy of the Gibbs measure at beta star vanishes. And that concludes. And that is the end of the proof, except a small point I have to add. So I repeat, we have just to calculate the sum of the two relative entropies to estimate this limit, assuming the lower bound saturated, and using the relation between the two entropies, we saw that all these are consistent only if the specific entropy of the Gibbs measure at the point beta star is 0. Point is, it is possible to go for other beta to have the same estimation. The answer for the moment is not. I have no idea how to calculate the specific entropy to all for every beta before beta star. I have, before finishing this proof, to comment on this hypothesis, because we supposed that the lower bound saturated. What happened in case, what happened if it's not saturated? Nothing changes. So if the bound is not saturated, that means that the entropy has already vanished before beta star. At beta star, we have the specific entropy 0, and the beta, the freezing temperature, is smaller than beta star. Now returning to the limit of the free energy, the tilted free energy, we can express now from this question, and which implies immediately for the real free energy, for the free quantity without any normalization, place this lower bound. If we use also the upper spherical bound for the model given by Comets in 1996, we have that the free energy at beta star must be between the two values. These bounds are the sharpest you can have at this moment for the model. Let me now go a step further and comment the result. We have shown that the model is frozen for every beta bigger than beta star. And what happened to the free energy, to the quantity free energy for every beta bigger than beta 1, for bigger than critical temperature? So the free energy must be in the blue region. The red line is the annealed. The upper line of the blue region is the spherical bound. What we have obtained here is the lower bound at the C, and by convexity we can go down, and so the Parisi solution must be inside, in the blue region. And if you like to see some more simpler. Let's see the other cases where the freezing temperature and the critical temperatures coincide. Take the case of the random energy model. Here, the things are simple because we have a critical temperature. It's bigger than 1 because the random energy model has a value of critical temperature which is bigger than 1. And the entropy vanishes at this point. So the freezing starts at Vita critical. And we can also apply the method to calculate the relative entropy at this point. And it turns out that the relative entropy for beta star, in the case of random energy model, it's much bigger than the relative entropy in the case of Shelton-Kilpatrick. This is natural because the REM is a completely uncorrelated model. So the correlations make that the relative entropy in the case of Shelton-Kilpatrick model is, at least for the point we can calculate, is smaller than the corresponding relative entropy of the REM. So let me just a second. Let me comment the results. What we have done. So we have shown that the entropy for all models considered, for instance, the mean field models like the REM, the multiplicative chaos, the random polymers or trees, and the Shelton-Kilpatrick models, the entropy of the associated Gibbs measure vanishes beyond temperature called freezing temperature, and this value is calculated by a simple geometrical trick. It is given by 4 times the logarithm of 2. We have obtained a formula for the low temperature free energy, which is much simpler than the formula given by the variational Parisi theory, and also we have used less ingredients. For instance, mainly what we have used in order to obtain this free energy is formula is essentially the convexity and the existence. We hardly we very used the existence of the free energy, the quencher energy, and the convexity. The low temperature. Now, what happened to the low temperature picture of landscapes and the hierarchy of levels presented in the Parisi theory? I conjecture that this range of the temperatures, this window of temperatures between 1 and beta star, is where we have many freezing transitions. The Gibbs measures are supported by fewer and fewer points, and we have what they call the replica symmetry breaking. So the replica symmetry breaking presumably occurs in between 1, the critical, and the freezing temperature. But this must be proved rigorously, of course. Thanks to this lower bound of the free energy, we can obtain easily a bound for the ground state energy, which improves the existing bounds, and it's very consistent with the numerical simulations. And also,
Flora, I'm sorry. So,
the duality relation. I was not aware of this duality relation. It was a remark of the referee of the paper, because there is a dual temperature defined as inverse of the temperature of the critical temperature of the REM. And if we can see that the value of the quencher free energy we obtained beta star satisfies this scaling relation. Just an information for in order to involve the duality temperature. And also, let me add that this same approach can be used to study the freezing in connection with the behavior of the multifractal spectrum of the log-correlated Gaussian fields. It is possible also to apply this approach in the case of random sparse sampling in the Gibbs weighted tree for constructing the initial structure of the measure at 1 via the study of the relative entropy. So if you know the relative entropy, you can have information about the initial measure. And I'm finishing with the challenge, which is to understand the relationship between the two formulae we have of the free energy, namely the variational Parisi solution and the one we have obtained in terms of the relative entropy. This is a very difficult problem, but it must be some relation to go from one formula to another is not be impossible, because after all, if the Parisi solution is given by a variational prism, you minimize over a sequence of measures. Now the formula I have obtained is just evolves the relative entropy. And we know from the large deviation theory that the relative entropy arises always after a minimization of some rate function. I think the relation is in this part, but I have no idea how to prove, how to pass from one formula to other. With this, I have just to thank you again for your attention, and we can I can ask to your questions. Thank you.
Thank you very much.
I'm also I have some time.
So, questions?
Yeah, can I ask a simple question?
Yes.
Yeah. So I think in this talk, the definition of freezing was that the specific entropy becomes 0. But then at some point you started mentioning that there can be many freezing transitions.
Say again, because the sound is very bad.
Oh, I'm sorry.
Maybe it's my computer. So the freeze, many freezing.
I can't hear you well.
Can you hear me well?
Yes, yes, perfectly. Yes, I can.
So actually, you didn't give precise definition of freezing in this talk, and you said that when freezing takes place, the specific entropy becomes 0. Yes. So I was assuming that was a definition, but in this discussion, you started mentioning possibility of many transitions. So probably there must be a different definition than entropy becoming 0.
So the freezing is just a general, just maybe what I have to say is that the freezing is the behavior, characterize the behavior of the low temperature phase of random systems. So the terminology of freezing initially comes from the fact that if you consider the free energy at low temperatures, you divide the free energy by beta, you get a constant. So it's somewhat a linearization of the free energy for temperature beyond a critical temperature. This is the first definition of freezing. Mm-hmm. If you see how the Gibbs measure behaves, you realize that in random interactions, the low temperature, the Gibbs measure is supported by very few points. So the extreme points, this is another characterization of the freezing, and the terminology here is the glassy phase. So the freezing is just the manifestation of the behavior of the free energy. Mm-hmm. And once you have this free energy behavior, normally there must be some behavior of the entropy because are related. And my question is, instead of characterize the freezing from the behavior of free energy, or from the domination of the Gibbs measure by the local extreme values, because it's always difficult. If there are any other manifestation or definition of freezing, you can handle, you can prove. And I proposed that regard the entropy. Is how the entropy behaves in the low temperature. For low temperatures, we know that the entropy decreases and eventually vanishes. That it is that sufficient to show freezing for the I'm not sure if it is sufficient to show freezing for all the models. At least it is sufficient to show freezing for the models, the mean field models physicists have studied. What I can say at this moment.
Okay, thank you.
I don't know if I answered your question, Hal.
And yeah, actually, you were mentioning the possibility of many.
The many is
then,
just
yeah.
What is the many freezing transition? Many freezing transition. What is it? Is a manner to say. Yes, I see what you talk about here.
Yes.
Yes. So in the theory of replica symmetry breaking, all that the system explores the landscape region, and so it goes to the different scales, and so maybe this can be interpreted, but I have no idea. For some many freezing transitions till the complete freezing. This is my saying, for instance, that the freezing starts some way at the critical temperature, continues smoothly till the freezing when the system is completely frozen. So it's gradual and not abrupt like the other models.
Okay, so your criterion can see the only final.
Yes, yes, I cannot because yes, all the final. And all the models beyond the particular value of beta star are frozen, including the SK model.
Sorry, but then what were these intermediate freezing transitions? They would be characterized by what?
They would be characterized by the what physicists say the replica symmetry breaking. So the replica are and also there is some possibility to go through this, because the entropy decreases with the beta. On the same time, we can, if you calculate, in some cases it's possible, the Hausdorff dimension of the support of the Gibbs measure, we see that we can obtain what is called multifractal spectrum. So the Gibbs measure, as the temperature is low, is concentrated to fewer and fewer points. That means the Hausdorff dimension of the support of the measure is changing, and this can be, eventually goes to zero, corresponding to zero entropy. I suspect that this replica symmetry breaking region has to do with the Hausdorff dimension of the support of the Gibbs measure. Because in the low temperature, yes, the Gibbs measure is supported by a few points.
So there is a question.
It's a fractal. There is a question, yes. I cannot hear.
Yes, so Jonathan has a question, right? Yeah, please go.
I have a question. Because you said that it's beta star, the system essentially is only at one minima all the time. Yeah, that's what you mean, concentration of measure.
Yes.
Now, since it happened before beta goes to infinity, it means that there are finite temperature for which the system stay localized in a single minima. It looks to me that it must say something about the barrier between the minima also. Yeah, because otherwise the system would be able to move from one minima to another.
Yes.
So the barrier should go to infinity at the same temperature or as a function of n or whatever. Yeah.
You're right. But I didn't consider this. It's very, very, very interesting point. Extremely interesting point.
Yeah, I think it's known for the Shelton-Kirkpatrick model. The barrier goes, I think they scale like n to the 1/4 or something, some power of n. So they do go to infinity. But I wonder for a realistic spin glass where the barrier cannot really become infinite, whether this would stay varied, this conclusion that the system freezes at finite temperature at no T. Yeah, because for the random directed polymer on a tree, for example, beta star is infinity.
No. The beta star is finite.
No, but is not infinity for the directed polymer?
For the directed you can consider it's not infinity. For the REM is not infinity. For multiplicative chaos is not infinity. It coincides with the critical temperature.
Oh, okay. Sorry.
Yes, and for this reason we don't speak about freezing temperature in this model. So we consider the critical temperature is enough.
Yeah, the free energy goes to 0 at T equal to 0. Sorry.
Yeah, can I ask a related simple?
Yes.
So what does this beta star in general has any physical meaning? Was this introduced only as a tool?
No, it's not. The physical meaning is it's not a physical meaning. It's just I cannot move. But the beta star comes when at beta star we have the relation between the two the two annealed free energies.
Yeah. I remember.
Because you do this. And the physical meaning behind this, there is a physical meaning because we have a relation between the annealed free energies. It is intuitively very appealing to say, okay, we have a relation between this free energy, this annealed. It must be some relation between the const. And we got the relation. That means the measure, there will be some relation between the measures. And we can write it to see because we can define the mapping passing for beta 1 to the beta star. And the mapping I saw it was at the level of limits, but it was the end of the calculation. We have to define this mapping at the level of the Boltzmann factors and to pass to the partition function to the measures and then to the limit. So there is, once you have seen this relation, it is here, we can again get here. So there is this relation, so the limit here, so this annealed is beta star times the annealed here. So there is the homothetic picture. This here, this A prime, B prime is the homothetic picture of A beta. And you can say reasonably, okay, there is a relation between the annealed means, is there any relation between the quants? Yes, indeed, here. And this relation can be translated by the relative entropy. Once we have this relation between the free energies, it must be some relation between the measures. And this is given by the relative entropy. But I think what is the most interesting here is this also. This relation, that we have a very intuitive formula for the quenched free energy for every beta in function of the quenched free energy of beta 1, a term which comes for the convex bound, plus the specific, not specific, the relative entropy. And this is readable as a formula, on contrary to the Parisi formula, which is very complicated to interpret the terms. Of course, the difficulty again is not possible to calculate always the S in order to have the graph. But I think the main challenge is to pass from this relation to the Parisi vice versa. This will be really very interesting, because here the physics is behind. If physically you can understand. I have the energy, the free energy at a certain temperature as a function of the free energy of one temperature plus a convex bound plus the deviation, the difference of the measures. This is much more speakable to a physicist or a mathematician doing some large deviations who have just the difference between the measures. And all the, and why I'm using the F to beta 1, because we know everything up to beta F, the F infinity of beta 1 is proved 87 and then many times again. And so we know everything at the high temperature, and we can express things as a function of the results of the high temperature. Otherwise, you have to pass through the heavy machinery of the Parisi solution. This is it was also a surprise for me when I saw this formula, and I think it's a real challenge how to show that the Parisi can be interpreted like this, or this can be interpreted like Parisi, but I have no idea for the moment. And the difficulty is here. The relation with the Parisi solution is coming from this term, from the relative entropy.
Yeah, thank you.
Other questions? Yes, no? I don't see. Maybe I have a quick question. So these results are for the SK model, or
and the other models, all the mean field models like the REM, or the polymers of the tree, and multiplicative chaos. But as the other models are more easy to prove, for the SK it was not known. For this reason, I have been concentrating in the proof of SK, just for for the mean field models we have studied the last years so commonly in physics. The models have some
what are the details
structure. Yes.
What are the details of the models that you need? Because it seems that actually then you really work at this level with convexity, and so it doesn't seem that you're using a lot of details of the model.
The models, you take the random energy model, you take the polymers on the trees, the Selektor-Kilpatrick model, and the multiplicative chaos model, and these models enter to this scheme. So there is nothing for this reason. I put a general image here, because you can write these models in a unified manner. We change every model has its Hamiltonian, and you can show the results. So you compare, if you like, in 2 lines, you compare the measures, the Gibbs measure at 2 different temperatures. You know very well what happened for the Gibbs measure at the temperature beta 1, and then you using a mapping to provided by this beta to relate. This is a functional relation between the measures and the temperature, beta star and beta 1. You know what happened with beta 1, and we express everything as a function of the relative entropy between the beta star and beta 1. What we can do in the large deviation case, we compare measures via the relative entropy. So that's all. So, and it turns out that we can obtain some interesting results, but it's just a comparison of the Gibbs measures at two different temperatures. Of course, you can see there is nothing work here. There you have no, don't use heavy machinery. No, because the work has been done, because up to beta 1 we have everything. For 30 years, you know very well the measure. So we can exploit this measure and to see how it's different, how it deviates for the other measures to at other temperatures. That's all.
Thank you. So I don't see any other questions.
I can check also.
So I guess, yes, I think we can stop. I mean, so we can close the official part of the seminar. I can close.
I can stop in sharing. Thank you.